Today I'll be talking about relations and its types. You have already studied about sets, Cartesian product of sets and subsets in grade 11, its representation and the relations. So let's talk about sets. A set is a well-defined collection of objects, and a set can be represented in two different ways. And the first method of representing the sets is known as roster form. In roster form, the elements of the sets are written in curly brackets and the set is represented as it is. For example, A equals to 1, 2, 3, 4, first four natural numbers. But sometimes it's practically not possible to write all the elements of a set. For example, if I want to represent all the rational numbers between two given numbers, it's almost impossible to represent it in roster form. In such cases, we use set builder form. Here is an example how in set builder form we represent a set. A equals to x, where x is a natural number which is less than 5. Now, Cartesian product of two sets. I'll explain with the help of an example. Let's consider we have a set A equals to 1, 2, 3 and 4 and set B equals to A, B, C. Now, first set has 4 elements, second set has 3 elements. The Cartesian product of A and B is defined as all the ordered pairs of elements of set A and set B, 1, A, 1, B, 1, C, and then 2, A, 2, B, and 2, C. Similarly, with 3 and 4, we'll make the ordered pairs. So, Cartesian product of A and B here is given by all the ordered pairs written in curly brackets. It means A cross B is another set of all ordered pairs. Now, let us consider we have another set C, which contains 3 ordered pairs, 1, C, 2, A, and 3, B, which clearly indicates that C is a subset of A cross B. So, any subset of A cross B is defined as a relation from A to B. This is the definition of a relation. Any subset of A cross B is defined as a relation from A to B and is generally expressed as relation R from A to B. Now let's take another example of a set P which consists of 3 elements, Jack, John and Mac, where Jack, John and Mac are 3 boys of same grade. Now the Cartesian product of P with itself is defined as Jack, 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 John, Jack, Mac, and John, Jack, John, 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 Mac, and so on. It will contain 9 ordered pairs, so P cross P will have 9 elements. And let's take another set which is Q, and Q is equal to Jack, Mac, Mac, John, and Mac, Mac. Clearly, Q is a subset of P cross P, hence I can say that Q is a relation from P to P. I can also say that Q is a relation on P. Now let me define another relation on set P, which is equal to A, B, where B is A's sister and A and B are elements of P. B is P's sister, but there is no girl in the given set, which means this R has to be an empty set. There will not be any ordered pair in it, or we can also say is equal to 5. Now my question here is, can we say that R is a relation on P? Since phi is a subset of all the sets, hence we can definitely say that R is a relation on P, and this relation is written as an empty relation which has no element in it. Now let's take another example. Let me define another set which is equal to S, and S is equal to P cross P. If I define it in set builder form, I'll say S is equal to A, B such that A and B are boys and both belongs to set P. Then S is equal to P. Since S contains all the elements of P cross P, hence this relation is known as universal relation. So broadly, relations can be divided into 2 categories. Number 1, empty relation, and the definition says that a relation R in a set A is called an empty relation if no element of A is related to any element of B, remember no element of A is related to any element of B, and this relation is always an empty relation. Fine. The second type is universal relation, which we have discussed. Here, universal relation is a relation in a set A where each element of A is related to every element of A, and the relation will be equal to Cartesian product of A with itself. And these relations are also known as extreme relations. Extreme means the first relation will have no element in it, and the second relation will have all the elements of Cartesian product. In addition to this, there are a few more types of relations which I shall discuss with the help of an example. Let us consider we have a set A which contains 3 elements 1, 2 and 3, and a relation associated with this set R which has 5 ordered pairs, and out of these ordered pairs you will observe these 3 ordered pairs 1, 1 is related to itself, 2 is related to itself, 3 is also related to itself. All the elements of A are related to itself. Such relations are known as reflexive relations. And here is another example, B equals to A comma B, and if I define a relation on this is equal to A comma B, and B comma B. In this relation also, you will find A is related to itself and B is also related to itself. All elements of B are related to itself in the given relation, and hence this is also reflexive. Now let's again take the same set A equals to 1, 2, 3. This time the relation R has 4 ordered pairs, and if you observe carefully, 1 is related to 2, and you will also find an ordered pair in which 2 is related to 1, means this one. Similarly, 2 is related to 3 and 3 is also related to 2. Such relations in which if A comma B belongs to R implies that B comma A also belongs to R, such relations are known as symmetric relations. Again the same set A equals to 1, 2, 3. This time a relation has 6 ordered pairs, and you will observe in this case if A is related to B and B is related to C, it implies that A is related to C. For example, 1 is related to 2 and 2 is related to 3, then 1 has to be related to 3. In this particular relation, such relations are known as transitive relations, and this has to be applicable to all the ordered pairs which belong to R. So we have talked about 3 more types of relations. The first one is reflexive relation. If A comma A belongs to R for all elements of a given set, such relation are known as reflexive relation, means every element is related to itself in a given relation. And second type is symmetric relation. If A1 comma A2 belongs to R, it implies that A2 comma A1 also belongs to R. Such relations are symmetric relations, means the first element is related to the second has to be related to first one. And the last type, transitive relation. If A1 comma A2 belongs to R and A2 comma A3 belongs to R, it implies that A1 comma A3 has to belong to R, means first is related to second is related to third, then first element has to be related to third, and it has to be for all the elements A1, A2, A3 which belongs to the given set. So this was all about 3 types of relations: reflexive, symmetric, transitive. And if a given relation is reflexive, symmetric as well as transitive, such relations are known as equivalence relations. in case if a question comes, prove that a given relation is equivalence, then what you have to do is you have to prove it is reflexive, symmetric, transitive. So let's see how to prove whether the given relation is equivalence or not. And here we have an example of a set of a relation R on integers given by R equals to a comma b, such that 2 divides the difference of a and b, a minus b. Let's try to understand this relation first. Here z is a set of integers and which can be expressed as -2, -1, 0, 1, 2. So all integers will be there, and similarly here also all integers. And if you observe, -2 is related to -2 because the difference is 0, which is an even number. -2 is related to 0 because difference is again even number and is divisible by 2. -2 is related to 2 also, and so on. So this mapping will give you a clear idea about this specific relation. All evens will be related to evens, all odds will be related to odds. Now question is whether it is equivalence or not. Equivalence means reflexive, symmetric and transitive. Let's prove one by one. For reflexive, I need to check whether a comma a belongs to this relation or not. Means b has to be replaced with a. Here a minus a I know is equal to 0 and 2 divides 0, which means a comma a belongs to this relation, which shows that a given relation is reflexive. Now let me see whether it is symmetric or not. For symmetry, I'll consider that a comma b belongs to this relation, which implies 2 divides a minus b. I can also write that 2 is equal to lambda times a minus b, which can be written as minus lambda times b minus a, which means 2 divides b minus a also. Hence b comma a belongs to the given relation. So for every a comma b belonging to this relation, b comma a also belongs to a given relation. Hence the relation is symmetric. Now the only thing required is we need to prove whether it's transitive or not. For transitivity, I need to prove that if a comma b belongs to R and b comma c belongs to R, it implies that a comma c also belongs to R. And for this, what I'm going to do is I will consider a comma b belongs to R and b comma c belongs to R, which implies a minus b equals to 2 times lambda and b minus c is equal to 2 times mu, because 2 is divisible by both the numbers a minus b and b minus c. Now if I add these two, what will I get? I will get that a minus c equals to 2 lambda plus 2 times mu, which can be written as 2 times lambda plus mu, means it is divisible by 2. Hence a comma c belongs to R. So we have proved that this relation is transitive also. And we know that if a relation is reflexive, symmetric and transitive, then the relation is an equivalence relation. So friends, this was all about types of relations. We have talked about empty relation, universal relation, reflexive, symmetric and transitive. And equivalence relation means a given relation is reflexive, symmetric as well as transitive in nature. So thank you friends. Next time I'll come with another topic related to relations and functions. Till then, thank you and have a nice day. And don't forget to hit like button, subscribe to watch more video. See you next